Hello and welcome back. In this video we'll be finishing up section 2.2 and we'll be looking at a couple of particular types of functions here. So a piecewise function is a function that's defined in pieces when you need different definitions of a function for different values of x. So let me define this using an example. So here in our example, a taxi charges $10 a ride for the first 5 miles. So it doesn't matter how far you go. If it's less than 5 miles, it costs $10. But then every additional mile after costs another $2. So if we let x be equal the miles ridden in the taxi, f of x, I need to define this, and for the first 5 miles it's just $10. So f of x is just going to be equal to 10 if x is going to be less than or equal to 5 miles, and typically we'd have to go at least somewhere in a taxi. So provided that we've gone any distance, anywhere from 0 miles to 5 miles, the taxi will cost $10. However, if we go over 5 miles, then we're going to start racking up a little bit more charge. So here, we'll still have to pay the $10 for the first 5 miles, plus a little bit extra. It'll be $2 per mile beyond 5. So how would I define this? If I've gone, say, 7 miles, I would need to take the 7 miles that I've gone, subtracted the 5 miles, and I know that I've gone 2 miles over. So if my total mileage is x, I need to subtract the first 5 miles to see how many miles have I gone beyond 5, and I'll take that times 2, because each mile will be $2. So this only applies, though, if we've gone more than 5 miles. So our function takes some values if x is between 0 and 5, and some other values if x is greater than 5. So let's evaluate our function. It's defined in pieces for a couple different values. So when f is equal to 2, when we're looking at f of 2, 2 is going to be x. So we look, do we use the first line or the second line? And we go, oh, 2 isn't bigger than 5, but 2 is between 0 and 5. So our function value is 10. Okay, so this is just the function value at that point. So let me erase this. Now, f of 7, well, now I need to look at this again, and we go, okay, do we use the first line? No, because 7 isn't between 0 and 5. 7 is bigger than 5, so we use this formula here. So this will be 10 plus 2 times 7 minus 5. 7 minus 5 is 2. 2 times 2 is 4. So the taxi ride would cost $14. This is how you use a piecewise function, and this is just an example of how we might build a piecewise function. So let's say that I'm given a piecewise function and I want to graph it. What might it look like? Well, I just have to go through this carefully and graph each section. So here, let's look at just the first line, and we'll only graph this first line, and we'll ignore the rest of this for the moment. For any x that's less than 0, our graph should look like negative x. So for x less than 0, which x values are less than 0? Anything on this side. So when we're looking at negative x, so let's plug in a couple of values. So g of negative 1, well, this is certainly less than x, so this is going to be negative 1, which is going to be positive 1. If I plug in a negative 2, it'll be negative 2, which is 2. If I do one more for negative 3, I'll get negative 3, which is 3. So we can see that this is going to form a straight line, and it will go something like this. But this is only defined for x is less than 0. So I'm going to put an open dot here to indicate that this part of the function doesn't count x is equal to 0. When x is 0, I use a different part of the function. So now let's look at the next part of the function. So for any x value between 0 and 2, my function is just 3. So the next part of the function is going to be between 0 and 2. So we're in between x is 0 and x is 2. And the function value is just going to be 3 the whole way. It doesn't matter if I plug in x is equal to 1, x is equal to 0.001, or 1.789. All of those values belong to here. So my function is just going to be 3 the whole way. So here's 3. My function is going to be 3 the whole way. Furthermore, when x is equal to 0, it is 3. So I'm going to put a solid dot there. Also, when x is equal to 2, my function is 3. So I'm going to put a solid dot there as well. And then finally, we've got x minus 4 is the function when x is bigger than 2. So for instance, if when x is 3, for instance, I would use this part of my function. So when x is 3, I'll plug this in here, and I'll get 3 minus 4 is negative 1. When x is 4, I plug this in here, and I'd get 0. So when x is 3, I have negative 1. When x is 4, I'd have 0. And if we were to keep doing this, we'd see that this is also a straight line. And it's going to go from here straight up. Now, again, because this isn't true, I don't use this part of the function when x is equal to 2. I use this line instead. I'm going to put an open dot there. So this is the function as it looks for this piecewise. This is the graph of this piecewise function. For x less than 0, I've got negative x, which is a straight line at this angle. X between 0 and 2, it's a constant function. It's just 3 the whole way. And when x is bigger than 2, it's going to be x minus 4. Again, a straight line. So this is fairly straightforward, but we just have to do it a little bit carefully. One type of piecewise function is called a step function, and it's a function whose graph looks like steps. So let's look at an example of what a step function is. So for instance, what's called the integer function. This is when you plug a number in, it looks at the greatest integer less than or equal to x. This is often called the floor function, and I'll explain why in a little bit. But let's plug in some values in here and see what we get. So if I plug in 2.5, I'm looking for the biggest integer that's less than or equal to x. So what are the integers? Integers are things like 0, 1, 2, 3, so on and so forth, or negative 1, negative 2, and so on. So it's the biggest one that's less than 2.5. Well, it's just 2. 2 is an integer. It's less than 2.5, less than or equal to 2.5, but the next integer, 3, is too big. So we cut it off at 2. If we look at negative 0.3, what are all the integers here? Well, we've got 0, 1, 2, 3, and so on and so forth, negative 1, negative 2, negative 3, and so on. This value is going to be negative 1. Why? Negative 1 is less than or equal to negative 0.3. If I draw my number line, I've got 0, negative 1, negative 2, 1. 0.3 is going to be about here. Negative 0.3. So the next integer, the greatest integer that's still less than this, is going to be negative 1. So drawing a picture, I think, helps with this function. When we look at this function evaluated at 1, it's just equal to 1. because it's less than or equal to. So if you plug in an integer, you just get that one. And then finally, this function evaluated at pi. Pi is 3.14159, and so on and so forth. So the next smaller integer is going to be 3. So when we graph this, we get something rather interesting. If you plug in a number that's going to be 0 point something, so let me call this 0.a. This is going to be between 0 and 1. So all of these values, if I plug them into my integer function, I'm just going to get 0, the next smaller integer. So let me do this in red. It'll be easier to see, I think. So any values between 0 and 1 are going to be 0. When I plug in a value between 1 and 2, I'll get these. And my function begins to look like steps. And we can continue backwards as well. So the closed dot is always on the left, because when you plug in an integer, you just get itself. So when you plug in 0, you get 0. When you plug in 1, you get 1. When you plug in 2, you get 2. The open dot will be on the right, because even though we might get really, really close to, say, 0, we're always going to drop down to the next smaller integer. So we just get this nice step function, and you can kind of see that this looks like steps.